Okay, some more examples or notes for section 7.2, and this is example number 4, and we're going to do this two ways. First of all, we want to find the area between the curve, and this is example 4 in your book, so you can take a look at this. This is over on page 393, so I drew a kind of quick sketch over here. This is y equals 0 on the bottom here. And we want to find the area using subregions, so find the area of the region R in the first quadrant that's bounded above by the line y equals the square root of x, and below by the x-axis and the line y equals x minus 2. So this region here, this whole region, and I broke it up into two subregions, A and B, but this whole region, A and B, is going to be bounded above by this line y equals the square root of x, and either y equals 0 or y equals x minus 2. Okay? And y is 0 when x is 2, so you can see that it intersects right there. So it goes up like this. Okay? So what we have to do is we have to break it up into two regions because we're taking the top curve minus the bottom curve, and my bottom curve changes. Here my bottom curve is y equals 0. Here my bottom curve is x minus 2. So region A was just the area, of the square root of x minus 0, so that's just that. So my bottom curve was 0, so that goes away. And here region B, the top curve was again the square root of x, but the bottom curve was x minus 2. And then the total area, it would be the sum of these two areas, region A plus region B. So we just take the antiderivative of both these and add them up. So this is going to be, I changed this to exponential form. A little bit easier to deal with that, and then that's going to be the antiderivative of that, be add 1, which would make that 3 halves, and divide by 3 halves or multiply by 2/3, and that's going to be from 0 to 2. And then this is going to be, again, x to the 2/3 times x to 3 halves, same thing. And then add 1, divide by 2, so x squared over 2, and add 1, which makes that x to the first divided by 1 is this, that. And we're going to evaluate that. So now we've got some arithmetic to do. So if I put 0 in this is going to go away, so I don't need to worry about 0, but I can put 2 in here. And this is going to be the same thing. It's kind of hard to, usually we do the root first, but this time we would just cube first, so we've got 2 cubed is 8 and the square root of 8. So it's going to be 2/3 times the square root of 8. So that was the easy part for this one. Over here it's a little more complicated, and I kind of ran out of room here, so here's the 4. If I put the 4 in here, the square root of 4 is 2, 2 cubed is 8, 8 times 2 is 16 over 3, and then 4 squared is 16 divided by 2 is 8, and then 2 times 4 is 8, so plus 8. So those are going to zero out. And then over in this one, negative, and then I've got the same thing now, just what I had over here, but I'm putting 2 in. So this is going to be the same thing as this was. So it's going to be another 2/3 the square root of 8. But I also have to put 2 in here, so 2 squared is 4 divided by 2 is negative 2, and then 2 times 2 is 4. So we can simplify this out a little bit. So we've got the 2/3 times the square root of 8, and 8 minus 8 is 0, so that's just 16/3. This is minus 2/3, and then this is negative 2/3, and then negative 2 plus 4, 4 minus 2 is 2 with a negative, so that's negative 2. Now these 2/3 square roots of 8's zero out, so I got 16/3 minus 2, which is 6/3, so 16/3 minus 6/3 is 10/3. So that's what we've got. Okay, so there's example 4, done in terms of x. Now, we can also do this in terms of y, and I did these on my notes, so this won't be as elaborately written, but hopefully you can follow it. And this would be probably the way I would do it, because I would only have to do one integral, because I can use my right curve minus the left curve, so I have to do this with respect to y. Because you can see we only have one set of rectangles to do. In the other form we had different tops and bottom curves. Here we only have one right curve and one left curve. Okay, in the previous example we had 2 different bottom curves, so that created the 2 integrals. Here we just have one right curve and one left curve, so we're going to use that second form I showed you. Right curve minus left curve, and if we go back to our notes, I think I can show you that where I gave you that somewhere in the notes. in that other form. Yep, can't find it now, but anyway, oh, here it is, it's right there. That's what I was looking for, right in front of me. So again, it's the right curve minus the left curve. And this would be respect in terms of y. So that's what you want to do. So let's take a look at this, see if I can get this done. So find the area of the region between this y equals the square root of x and y equals x minus 2. Now the thing is, it has to be in terms of y, so everything has to be in terms of y. Now if we look at this, what we're going to do is we're going to integrate this. We know our points because this is y equals the square root of x. So we want to find this region from 0 to 4. Or in this case, it's, in terms of y, it's going to be from 0 to 2. All right, so I'm going to sum these up from 0 to 2. And I can tell that this is going to be 0, that's my lowest y value, and 4, 2 is this point, so that's my highest y value. So I'm going to go from 0 to 2. And remember, that's in terms of what's happening with the y. Okay? And everything has to be in terms of y, so y equals the square root of x. So if I square both sides, I get y squared equals x, or x equals y squared. So that's going to be my left curve. And then if y equals x minus 2, then if I just add 2 to both sides, x equals y plus 2. So that's going to be my right curve. So this is my right curve minus my left curve. Okay, so take a look at that. Right curve minus left curve. And this is going to give me the length of this rectangle would be whatever this value is minus that value. In other words, this whole value minus that value would give me that value. That's going to be the, if I look at it sideways, the height of my rectangle. And then delta y, my change in y, will be the width. If we go back and look at our Riemann sums. Okay? And we're going to sum up all these rectangles from 0 to 2. So there's your right curve, there's your left curve, and we have this in terms of y. Now see, y squared would look like this. We'll talk about that a little bit later, about these relationships, these parabolas that are symmetrical with the x-axis. We don't usually deal with those because they're not functions, but we can deal with them when we're finding areas, their relations. Okay? So once you set up the integral, the rest is pretty easy. Again, if we take the antiderivative of this, first of all, I wrote this in descending power, so I wrote this as 2 plus y minus y squared. Didn't really have to do that because you're going to evaluate it just by convention. And we take the antiderivative, so that's going to be 2y, y squared over 2 minus y cubed over 3, and I'm going to evaluate that from 0 to 2. And using your good old fundamental theorem of calculus, if I put 2 in here, that's going to be 2 times 2 is 4. 2 squared over 2 is 4 over 2. And then 2 cubed is 8 over 3. So that's 8 thirds. And then if I put 0 in it, there's a y factor in each of these, so that would be 0. And again, this would be your f of b minus your f of a. F of a just happened to be 0. Okay? And then this ends up being 4 plus 2 minus 8 thirds. So that's 6. Okay, 6 minus 2 thirds is 3 1/3. And 3 1/3 is 10 thirds, and that's the same thing we got, just a different way of doing it. Okay? So that's changing everything in terms of y. Now take a look at this, because this can be, a little bit, intimidating at first, because you have to make sure you get everything in terms of y. Your limits have got to be in terms of y. So you have to do a lot of shifting around. And then you've got to change your curves from x to y. Okay? So again, spend a little bit of time with this one. Make sure you kind of thoroughly understand what's going on, because that's a good technique that you must know. You must know how to change them in terms of y.